Hello and welcome to the presentation on how gases exert pressure, part 2. We're going to be looking at how we derive the ideal gas law from the three equations we came across in the previous video, and then learn how to use that ideal gas law in two simple cases. Okay, so the ideal gas equation. In the previous video we looked at how we found Boyle's law, the pressure law, and Charles's law. You can combine all these equations. I'm just going to rewrite them because pressure times volume is equal to a constant, but it's a different constant than pressure divided by temperature for a fixed amount of gas. Okay, so I've renamed these constants CT, CP and CB and just put it into letters so it's easier for me to mess around with. Right, if I multiply 1, 2 and 3, P times V, that's that bit, P over T, V over T and so on, and CB, CP, CT. Okay, I can simplify this to P squared V squared over T squared, and I can now take the root of this, because basically P squared V squared over T squared is the same as PV over T times PV over T, or the same as PV over T in brackets squared. So I can take the root of that and take the root of the other side to get PV over T is equal to the root of CB, CP, CT, which is equal to a different constant again. Okay, but the point is that it's constant. Pressure times volume divided by temperature is equal to a constant. Because of that, you can write this equation the same as we did in the previous video as a before and after equation. Pressure before times volume before is equal divided by temperature before is equal to the same figures after. So now we can have a situation where we have a before situation, say a balloon at sea level at a known temperature, and then it's moved to a very greater altitude, top of the Andes, let's say. The temperature is different and the pressure is different, and we can calculate the new volume, which is very useful. Let's look at an example. You should be able to do this if you've done the previous video, so if you pause the video now and have a go at it, I'm sure you can do it. Okay, so first things first, write down the formula. Go through the question, making sure you get the correct numbers you need. So let's have a look. We've got a initial volume, 20 meters cubed at an initial temperature. So this is volume before, temperature before, and pressure before. It's heated to a new temperature, and its volume is allowed to increase to 30 meters cubed. So we've got a new temperature and new volume, and we've been asked to calculate this new pressure. So we've got all the numbers we need apart from one, which is the one we're going to have to calculate. Notice as well that the temperatures are in degrees Celsius. We'll have to convert those to Kelvin. So add 273 to them to convert them to Kelvin. So all I've done here is substituted the numbers in. Now I'm going to have to rearrange to get PA on its own. So let's have a look. If I multiply both sides by 273 plus 500 here, that means I can cancel it out on this side, and I get 273 plus 500 on the top line of this one. And then divide both sides by 30. Okay, so I rearrange, and dividing both sides by 30, cancel out on this side, I get to this state. Okay, is equal to PA. Calculate it. My new pressure will be 5.2 times 10 to the 5 pascals. Hopefully you've been able to follow that. If not sure about any of the steps, post a comment on YouTube, or you can check out Khan Academy for any of the rearrangement type stuff. Okay, example 2. Pause the video and read this question. It's a little bit trickier, this one. Well, maybe, but I'm sure, again, if you're careful and you think about it carefully, you can work it out. Okay, so here we're talking about a gas cylinder contains 0.1 meters cubed of helium at a pressure of 16,000 kilopascals. The gas is used to blow up balloons. The balloons each have a volume of 0.4 meters cubed when fully inflated at a pressure of 102 kilopascals. So there's a pressure change and there's a volume change. The temperature remains the same throughout the whole process. Calculate how many balloons can be filled. Okay, actually the temperature remains the same. This means I could just use the Boyle's law. But I can use the ideal gas equation, and because it tells me temperature remains constant, I can just cancel out the temperatures either side. Because TB is equal to TA, I can cancel out the temperature, and I just get back to that Boyle's law anyway. So if you want to just simplify your life and remember less formulas, just remember the ideal gas equation, and then when you find temperature is constant, you can just cancel it out, or volume is constant, you can just get rid of it, and you're left with pressure over temperature before and after, and that makes life a lot simpler. Okay, so it's a before and after question. Now, because it's a bit of a trickier question, I'm going to draw a picture. Whenever I don't understand something very well or I find something difficult in physics, I just draw a picture to try and simplify things. So we have a cylinder before, and we have a number of balloons, but we don't know how many balloons we're going to have afterwards. The cylinder is at a pressure of 16,000 kilopascals with a volume of 0.1 meters cubed. The balloons are at a pressure of 102 kilopascals with a volume of 0.04 meters cubed each. So I'd have to multiply that by the number of balloons to get the total volume. So if there's 1,000 balloons, it will be 1,000 times this number, but I don't know how many balloons there are yet. Okay, it tells me that the temperatures were the same, so that means temperature before is equal to temperature after. Okay, so I've got all the figures I need now. Let's look at the formula. I can get rid of temperature, as I said earlier. I can cancel it out because TB is equal to TA, multiply both sides by TB, and then I can cancel them. So I'm just left with Boyle's law. Stick in the numbers I have. 16,000 kilopascals times 0.1 meters cubed is the pressure and the volume before. The pressure after, because every single balloon is going to be at 102 kilopascals, and each individual balloon has a volume of 0.4 meters cubed, but I don't know how many balloons I've got, so the term I can put in for volume afterwards will be 0.4 times the number of balloons afterwards. Now divide both sides by 102 times 0.04. I can cancel it from this side, and I'm left with a term that gives me NB. NB is equal to 16,000 times 0.1 divided by 102 times 0.04 equals 392 balloons. Okay, hopefully you found that. You could follow that. If not sure again, just post comments. Okay, thank you very much for watching. You should now be able to complete steps 1 and 2 here, or understand steps 1 and 2 here.